off the Greenland ice sheet, and we're sort of interested in how the atmosphere, the ocean, and are impacting the loss of ice from these two big glaciers. And I want to focus on two structures that you can see here in the Denmark Strait. There's two notches that develop in the sea ice, one just off of Sørmark Fjord, the other one just off of the Kangerlussuaq Fjord. And this is going to be sort of the focus of attention today. So again, air sea fluxes play a really important role in water mass modification in the region. There's a long history of using real analysis products to try to characterize the spatial and temporal variability in these fluxes. I'm going to look at a new high-resolution 2.5 kilometer 32-year-long record of a regional reanalysis to look at this variability along the Denmark Strait. By comparison, the first of these studies was done a while ago with NSEP reanalysis, which had a scale of 200 kilometers. So obviously, we've got a lot more view of the structure recently. And so as I'll talk about it, the retreat of sea ice in these regions is associated with these notches offshore these two big fjords. And we're sort of interested in how these notches develop and how they're evolving over time and what impact they have on the marine terminating glaciers. So this is a paper that we wrote up about a decade ago, looking at essentially this notch off of the Kangerlussuaq Fjord. And what I'm showing here is the sea ice, mean sea ice concentration in the winter and the 400-meter isobath. And so as you can see, this notch in the sea ice developed along the northern or the kind of eastern boundary of this trough, which extends offshore of the Kangerlussuaq Fjord. And so the idea was that essentially topographically controlled Atlantic water is flowing into the trough and towards the fjord, and that's leading to the retreat of sea ice in this region. There's been a lot of work on essentially the role that the atmosphere plays in forcing this Atlantic water onshore into the fjords. And there's a paper written a couple of years ago. And essentially the argument is that the typical flow in this region, what is typically called barrier flows, the flows are from the north down along the coast here. And when they reverse, actually, it's reversal that actually drives the Atlantic water up towards the face of the glacier, where it contributes to the melt of the glacier. And so this is the basic idea, is the winds are essentially controlling the influx of this Atlantic water up onto the fjord. So what I want to do here is I want to use this new regional reanalysis of the Arctic. There's actually two domains, one around Greenland and one around Svalbard in the Barents Sea. It's called CARA, the Copernicus Arctic Regional Reanalysis, and it's based on an NWP product called Harmony, which is used operationally by the Danish and the Icelandic Met offices. The model is non-hydrostatic and has a resolution of horizontal resolution of 2.5 kilometers, temporal resolution of 3 hours. We have data from 1991 to the present, and I'm going to focus on March, because March, of course, is the month when the sea ice tends to be at its maximum. As I'll show you, one of the challenges in using any model is that the air sea fluxes may have issues with them. And as I'll show you, the CARA fluxes are biased high. It's probably related to how the model represents the heat and moisture coefficients in the parameterization. And so as a result, we won't actually use the model fluxes directly, but we'll use the bulk fluxes that we generated using the model surface fields. I'll also use the climate data record from the NSIDC. For validation, we have two buoys that were deployed in the region, a Dragon buoy back in 2007 to 2009, and then we had a field project in 2018 called the Iceland Greenland Seas project, and we deployed a buoy for just a short period of time. It broke loose of its mooring and drifted off, unfortunately. That's the buoy when it was being deployed, and if you look carefully, you can see it off in the distance there. And again, what I did is I used essentially the bulk fields from the buoy data, again, to generate estimates of the turbulent heat flux. So this is essentially sort of two snapshots back in the 1990s, and then more recently, this is sea ice extent off of in the Denmark Strait region. These are the two buoy locations here, and you can see the notches They were present back in the day, but they've become much more pronounced recently. There they are. And so if you look at what's happened actually with the retreat of sea ice, is that there's been a thinning of the marginal ice zone. So the marginal ice zone is getting thinner now. Essentially, the ice cover back towards the coast has really not changed much, but we're just essentially making a much thinner marginal ice zone. And so you see these notches are much more developed now than they were back in the day. And if you look at these two boxes here, all I've done is just average the sea ice concentration over these two boxes. And this is what you get. So you can see there's a Sermlik Fjord. This is the Kangerlussuaq Fjord. And so you can see in both cases, there was a period of time when the sea ice concentration was approximately constant, but of course varying. And then that was followed by a time when there was a steady retreat or reduction in the sea ice concentration. And you can do a breakpoint analysis and figure out that this breakpoint for the Sermlik Fjord occurred around 1990. The trend after that is significant. And it occurred a few years later for the Kangerlussuaq Fjord. So again, I'm going to focus on the Dragon Buoy location. Very similar results occurred for the Icelandic Greenland Sea Buoy location. And so what I'm plotting here are scatter plots. In this upper quadrant here, I'm plotting the observed bulk flux from the buoy. And on the y-axis, I'm plotting the turbulent heat flux. That is the sum of the sensible latent heat fluxes derived directly from the model. In this here, I'm doing the same thing, but now I'm using the bulk fluxes from the model. And here I'm just essentially comparing the model to the bulk fluxes. And so what you can see is that there's this region when I use the model fluxes where consistently the model fluxes are much higher than the observed fluxes, okay? That doesn't happen so much with the bulk fluxes, right? So there's this bias towards higher heat fluxes in the model compared to observations for very high heat fluxes. And you can see that also here, where I plot now the model versus the bulk fluxes. And of course, this line is the one-to-one line. And so if the two agree, they'd line right along here. And so you can see that for low heat fluxes, they do agree. But again, for higher heat fluxes, there's this nonlinear fit where now the model is generating much higher fluxes than you get from the bulk, okay? And again, just saying that again, there's this, you can also look at the slope here. The slope for this comparison is 1.1, which means again that the model fluxes are higher than the observed fluxes. The slope when you do the bulk fluxes, again, is close to 1. There's a reduction in the RMS error as well. And then you can also see this non-linearity here. So for this reason, I'm going to focus on looking at the bulk fluxes from the model rather than the model fluxes. And we don't really understand why. The same thing happened in the first analysis they did with the NCEP reanalysis. The NCEP reanalysis fluxes were biased high, and it was because the exchange coefficients they had used in the model were not appropriate. And so obviously the same thing's probably happening here, but we don't actually understand exactly why we have this bias. So what I'm plotting here is essentially, I'm now looking at the changes. So I'm focusing on the early decade and the later decade. This is the change in the sea ice in the model. And again, you can see there's this large region where there's essentially been just a retreat. The marginal ice zone is getting much narrower. We've lost upwards of 60% of the sea ice concentration along this band here. Inshore, again, there's no loss of sea ice. So essentially, the marginal ice zone is just getting thinner. And again, you can see in the region of these two notches, there's this sort of extension of this region of loss towards the coastline in these two regions here. And this is now is just the change in the turbulent heat flux later versus the earlier. And what you can see is that along this region where there's been a loss of sea ice, there's been an increase in the heat fluxes. And that makes sense because we're removing that sea ice, which acts as an insulator. We're now exposing ocean, which has never been exposed before to the atmosphere. And so there's been an increase in the heat fluxes. And you notice these increases are largest, upwards of 75 watts per meter squared, again, in the region of these two notches. So these notches are regions where there's been a much larger increase in the heat fluxes in this region here. And then offshore, you'll notice that there's been a reduction in heat loss. And again, that's what we expect to see happen, because as the sea ice retreats northwards, it draws the region of highest heat fluxes towards the coast as well. And then one gets a reduction in the heat fluxes offshore. So this has also been observed in the Nordic seas as well. So again, just to these two results then show that there's been this retreat of the sea ice with these amplified notches in the location of these troughs offshore of these two large fjords. And there's been an onshore increase in the heat fluxes and an offshore decrease. And these, again, I didn't show you the magnitudes, but there's been upwards of 50% increase in the magnitude of the heat fluxes in these regions here. So just to conclude then, so over the last 30 years, there's been these changes in the sea ice distribution. They impact the air sea heat fluxes. CARA allows us now to really get a fine scale view of that. So the sea ice retreat in the Denmark Strait has resulted in this onshore increase and an offshore decrease. This has been noticed before, is that the retreat of sea ice in the Nordic seas to the Greenland Sea to the north has reventilated the East Greenland current. And so the same thing is now happening farther south as well. And I didn't show this, but the CARA also does a much better job of representing the variability in the winds along the strait here. And so the basic idea is we have these two notches, we have these topographic troughs offshore, and the idea is that the warming Atlantic water is able to topographically flow up towards these fjords along the eastern boundary. And that's the thing which is driving this localized loss of sea ice in these two regions. So thank you very much, and I'm happy to answer any questions.
Thank you, Kent. That was great. So if anyone has questions, please feel free to put that into the chat box on EventMobi. Right now, I don't see any questions in the chat box, but we'll give it a quick minute. And oh, I see a question from Amber. Are there implications for marine heat waves in the future?
That's a really good question. I don't know the answer. I've never looked at marine heat waves, but obviously, these areas are warming. The SSTs are warming as well. Of course, the retreat of the sea ice allows the SST, allows the warm water to also move onshore. So it could be impacting heat waves in this region, but I actually haven't looked at that problem.
We also have a question from Yo-Yu Liu. Is CARA a coupled atmosphere-ocean ice model?
So it does have an ice model associated with it. And one thing which is novel for reanalysis is that most reanalyses like ERA5 have a fixed sea ice thickness, usually 1.5 meters. CARA has a variable thickness ice model, but it doesn't have a coupled ocean model. So the ocean SSTs are just prescribed. But it does allow one to see the effect that thinning sea ice is having, because of course, as the sea ice thins, of course, it's easier for heat fluxes from the ocean to get through the atmosphere. So it does have a sort of a bit of a coupling to the sea ice, but nothing to the ocean.
And Paul Myers asks, how does CARA compare with ERA5 or other products in the region, thinking about driving an ocean model?
Yeah, so that's a really good question. So I didn't show it, but essentially, CARA agrees really well with ERA5 when you're offshore. When you get onshore, of course, the complex topography of Greenland is better represented in CARA at 2.5 kilometers and in ERA5 at 25. So onshore, you tend to have better representation of the winds, but offshore, the winds actually are quite reasonable. And actually, I have a student who's supposed to come next, but he hasn't arrived yet. He's in Europe, so that may be the problem. But he was going to talk about exactly that problem. So maybe we can put him in later and he can answer some of Paul's questions.
We have one last question from Yo-Yu. What is the spatial resolution of the ocean ice model?
So the ice model is at 2.5 kilometers as well.
Okay, perfect. Thank you so much. So, as Kent just mentioned, we are actually currently missing our second speaker. So, I think what will do if Alexandra is amenable is we'll move on to our third speaker, Alexandra Stephens, and so she can go ahead and share screen.
Okay. All right. Just give me a second to move some Zoom stuff out of the way so I can see what I'm doing here. Okay. Hello.
So right now we are seeing presenter view. So you probably just want to switch presenter and full screen. Perfect. Looks good.
Okay, so I don't know. I thought it would just share this while I was on the other part, but that's why I have my notes printed as well. Hello, my name is Alexandra Stephens. I am a graduate student at the University of Toronto, supervised by Professor Kent Moore, and our group studies the Arctic climate system. Today, I will be talking about the characterization and impact of extreme winds in the Nares Strait. During this talk, I will first start with an introduction to the Nares Strait and the specific event that we are studying. Then I will describe the data sets we are working with and our analysis methods. After that, I will show some results from this work, draw some conclusions, and finally, there will be some time for questions. So my animations are not working apparently, but the Nares Strait is located between Greenland and Ellesmere Island in the high Arctic. You can see where it is on the map here. It is narrow with steep topography on both sides of the strait. In April 2005, there was an ice camp set up near Crozier Island to study the strait, but a severe windstorm beginning April 13th destroyed it. The wind speed observed at the surface reached up to 25 meters per second, and on the figure, Crozier Island, which is the approximate location of the camp, is marked by this large red X. Here is a satellite image of Kennedy Channel, which is part of the Nares Strait, the part of the Nares Strait where the camp was located. You can see Greenland in the east, Ellesmere Island in the west, the Lincoln Sea to the north, and then Robson Channel, Hall Basin, Kennedy Channel, and Kane Basin as you go south through the strait. Next to Franklin Island, the pinned location represents the approximate location of the camp. And in this figure, you can see a tent from the camp that was destroyed by the windstorm. For this work, we have used the Copernicus Arctic Regional Reanalysis, also known as CARA. So let's compare this regional reanalysis to the better known global reanalysis product ERA5. CARA has twice the number of time points per month on account of it being 3 hourly, whereas the ERA5 data we were using is 6 hourly. CARA has 21 height levels between 10 meters and 2 kilometers. The ERA5 data we're using only has 2 height levels, 10 meters and 100 meters. The selected CARA grid is 435 by 386 polar stereographic grid with approximately 2.5 kilometer spacing. The ERA5 grid we have selected contains 41 latitude rows and 141 longitude columns with a quarter of a degree spacing between them. This means the latitude rows are about 28 kilometers apart, whereas the longitude columns are approximately 5 kilometers apart over this region. We will see both of these grids on the next slide. So this comes out to a total of over 800 million data points per month for CARA, but just over 1 million for ERA5. The consequences of the difference in resolution are that CARA resolves topography better, which means it captures the faster topographically forced winds that ERA5 does not. Here's a visual comparison of the CARA and ERA5 topography fields. The first thing you notice is that the CARA map has a much better resolution than the ERA5 map. The CARA map captures the steep topography of both sides of the strait. You might notice the CARA data for Ellesmere Island shows the maximum elevation of Barbeau Peak, for example, while ERA5 does not. Similarly, ERA5 does not show the minimum elevation of narrow fjords or part of Kennedy Channel in the Nares Strait. According to ERA5, there shouldn't be any water there. So we used all data from the month of April between 1991 and 2022 for the climatological analysis. We compared the data from the April 2005 storm with the 95th percentile for each point in our three-dimensional mesh and focused on April 14th at midnight coordinated universal time because that is when the winds were strongest near the ice camp. This would have been in the evening of April 13th for the ice camp's time zone. The plots created include profiles and time series using the closest Kara grid point to Crozier Island to approximate the ice camp's location, cross-sections at the latitude of Crozier Island, and maps at single height levels at various map scales. So on the left here, you can see the time series at the closest Kara grid point to Crozier Island. The x-axis is time and the y-axis is height. The color contours represent the wind speed at each point in height and time, and the somewhat transparent gray shading over top of the color contours indicates where the winds exceed the 95th percentile. As you can see, the winds reach their maximum speed on April 14th at midnight UTC, so we'll be focusing on this time point in more detail. Now, in the right plot, you can see this wind speed profile with wind speed on the x-axis and height on the y-axis again. The dotted colorful lines are the 1st, 5th, 50th, 95th, and 99th percentiles respectively, and the solid black line is the data from this time point at the Crozier Island coordinates. We can see that the maximum surface wind speed was about 15 meters per second. It does not exceed the 95th percentile. We can also notice a low-level jet over here. Between the 700 and 800 meter levels, as well as that the profile just touches the 99th percentile around the 1 kilometer level. So as you can see in the right plot here, we're again using the closest points to the 80.5th parallel here, and the points are about 1/10 of a degree apart from each other. This is about 1.8 kilometers at this latitude. Also of note is the steep topography on both sides of the strait, as seen in the cross-section on the left, especially the Ellesmere Island side. In the left plot, we're using the same color bar as in the previous slide's time series plot and the same shading scheme. You'll notice that a lot of the cross-section is shaded. Additionally, you can see the low-level jet previously found in the profile. Its maximum here is found above Greenland, and it's approximately 25 meters per second. Here are the winds at 10 meters above sea level on the left and 700 meters above sea level on the right. Once again, we're using the same color contour scheme, but for these plots, we've not included the shading. In the 10-meter plot, you can see a strong ageostrophic component in certain places in the strait. At some points, the wind vectors cross perpendicular to the pressure coordinates, which are shown here in units of hectopascals with spacing of 0.5. The ageostrophic winds can be much more intense than the geostrophic ones. On the right, you can see the winds are much stronger at the 700 meter level. The maximum wind speed at this level for this domain is about 28 meters per second. Despite more of the area being open at this level, you can still see strong channeling down the strait, which shows how important topography is here. Note that we don't have a vertical component of the wind here. So this was originally supposed to show first a plot without the shading and then a plot with the shading. So you'll just have to imagine what it looks like without the shading. Here we have a wide view of the Nares Strait. We're using the same color contours again. And the highest wind for this entire domain is about 29 meters per second. You'll note that some of the fastest winds have a strong ageostrophic components again, as these wind vectors cross the pressure contours perpendicularly. And the pressure contours have 2 hectopascal spacing here. And then with the shading added to this plot, you can see the winds exceeding the 95th percentile at many places at this time point. Now, some conclusions from this work. The winds exceeded the 95th percentile at certain places and times, including on April 14th at midnight UTC at the 700 to 800 meter levels for Crozier Island, the approximate location of the ice camp described in the Melling 2011 paper. However, the winds at the surface do not cross the 96th percentile. Our analysis shows a similar timeline to the Melling paper mentioned. However, the most extreme winds, which Melling's team observed, are still not captured by CARA at this resolution. The CARA maximum surface wind speed was about 15 meters per second, while Melling's team observed a maximum of 25 meters per second. And knowing that CARA represents a significant improvement in the ability to capture these extreme winds over ERA 5, perhaps even better resolution might capture winds closer to the observed maximum. Thank you very much for your attention. I'll now take questions if there are any.
Thank you very much, Alexandra. That was really good. So while we wait on questions in Event Mobi, I do have a question, but just before that, I'm going to make a quick request that if our host is online, if they could please promote Adrien to a panelist. Okay, so for my question, you had just mentioned in your conclusions that with an increase in resolution, you might get even closer to those maximums. So I'm wondering, with an increase in resolution, what other differences do you think we might see? Like, is there a lot to be gained if we were able to go to an even higher resolution, or are we most of the way there with CARA?
I'm not really sure. It's a good question. I think there is definitely something to be gained in modeling more of the extreme winds because we might be able to say more definitively that this is a normal event for the region, with normal being defined as less than 95th percentile, for example. As it stands right now, since we can't model those winds, we can't tell if the observed winds are really extreme or not. And according to this analysis, the winds that CARA found for this time point in this location were not extreme for the CARA climatology, but it's possible if we could include all of the winds as they actually happened, that we could either find that they were extreme or that they weren't.
Thank you. Yeah, that makes great sense. So I don't see any questions in the chat yet. We do have a couple of minutes. And I'm hoping after that we'll be able to move to the speaker that was going to be our second speaker, who would now be our third speaker, but we are just sorting out some technical details there. So if everyone can bear with us for a couple minutes. And again, yeah, if you have any questions, please feel free to put them in the chat box on Event Mobi. And just in case we can't get Adrien online, Lee, would you be comfortable presenting if needed?
Yes, sure. Yes.
Okay, great. So what we will do is we'll just give it a couple minutes. Oh, here we go. I see Adrien. Fantastic.
Hello.
Welcome, Adrien. Okay, so in about 1 minute here, we will move to Adrien's talk if he is ready to share his screen. Okay, cool.
So should I stop sharing?
Yeah, I think we are probably good. Thank you again, Alexandra. Okay, so our second and third speakers have been swapped in this session. So Adrien was originally going to be the second speaker and is now the third speaker. We're very happy to have him online to give his talk. So Adrien, whenever you're ready, please feel free.
Cheers. Thank you so much. Yeah, sorry about the technical difficulties. Don't know what happened there. Good afternoon, everyone. Today we'll be presenting results from a comparative study that's currently taking place with the University of Toronto. So we studied the structure of tip jets, which was mentioned previously, topography-induced high-speed winds, using a new reanalysis model, which we previously already talked about. And the focus is primarily on southern Greenland, where we have the highest tip jets on, well, actually on the whole ocean surface. So it's quite interesting. So the objective of the study was to determine if this new model more reliably modeled the spatial variability of high-speed winds compared to preceding models. So I'll be giving a brief summary as to why we care about these high-speed winds in the first place. We'll also take a look at the data sets used to accomplish the study. Then we will take a look at topography between models to better infer results later on. And then we'll obviously look at the arguments presented in this study, where the study was initialized with direct comparisons between reanalysis models first. And afterwards, we did comparisons with in situ measurements to, I guess, determine if the model was reliable in the first place. So why do we care about high-speed winds? High-speed winds typically lead to an increase in heat flux from the ocean to the atmosphere. Typically, if you have cooler winds, heat from the ocean kind of extends to the atmosphere. So this has implications for ocean surface cooling and leads to weakening of ocean stratification. This weakening in ocean stratification often leads to vertical mixing, which has implications for larger ocean circulation patterns. There's also the areas of interest for harnessing wind energy, and maritime traffic is also deeply concerned with these wind speeds. So it is quite important to categorize the tip jets coming off of the southern tip of Greenland. And this image here is not too relevant to this study, but I guess it does kind of capture the increase in wind speed at the very bottom, which is subject to westerly and easterly tip jets. So what are the data sets we're talking about? So we have this new high resolution model, fairly new. I think it's 2 or 3 years old now, but 2.5 kilometer resolution, horizontal resolution for 10-meter wind speeds, which is the main focus. And the data ranges from 1991 to 2022. Actually, it's fairly, it updates every month, so it's probably more recent than that now, but that's the scope that we focused on, 1991 to 2022. And we're comparing primarily with the ERA 5 model, which has been talked about previously. For the horizontal surface resolution, we're looking at 31 kilometers. And there's various weather stations. So these are in situ measurements, weather stations, and buoy data as well, 2 buoy data. So that's that. So let's look at the topography difference between the models. So this is ERA 5 here. As you can see, quite pixelated, does not capture the coastline very well. And this is Kara. So as you can see, coastline is much more detailed. We can see the difference immediately. And we also have a 100-meter resolution for this one. So a bit more detailed. There's definitely progress to be made, but that's that. So the main study. So the original, to better visualize where the largest differences in 10-meter wind speeds between the Kara and ERA 5 models were, we did scatter plots at each spatial point from the previous images that I showed. And we subtracted it by 1 to get kind of a heat map. So if you're looking at 1-to-1 slope, that's typically, as you can see, this is the top image here. They agree. But in some areas, we actually have this slope on the bottom, and this is Kara over ERA 5. And so this is the result that we get. So as you can see on the bottom here, the bottom scatter plot, very large slope difference. And Kara is actually, not overestimating, but has much higher wind speeds than ERA 5 in most cases, especially along the coastline, which is where we have the largest differences. We have slope differences of nearly 600%, so 7 slope. And yeah, as you can see, all along the coast, not in the ocean, which is very important for later on, I guess. So further evidence of the preceding arguments is presented in this figure here. In this plot, wind speeds are collected by 10-meter wind speed data from the OOI buoy, which is that little black circle that you can see on the screen. So we filtered for time and dates based on the 95 percentile of the OI wind speeds, and we got these images. So as you can see, over the ocean, not many differences, same general pattern, but along the eastern coastline, we actually have much more detail in the Kara model. I should note that for 95 percentiles, Kara does actually have the tendency to have 1 to 2 meters a second more, but the same general pattern applies over the ocean. So I hope that's pretty clear. So to determine which of the two models were more reliable compared to in situ measurements, both models were compared to weather station and buoy wind speed data. In general, Kara agreed with in situ measurements much more over the coastline than ERA 5, but both models tended to agree with the in situ measurements on flatter terrain, which we saw previously. There's not much differences in interior Greenland or over the ocean. So there's that. There was, however, slight discrepancies between the buoy data sets, or one of the buoy data sets, the OI buoy, which prompted further analysis. So this is the plot that we have here. As you can see, for Kara and ERA 5, they both tended to overestimate wind speeds, especially in the higher percentiles. And this becomes evident with these plots here. So this one is a kind of like a 1-to-1 slope, as you can see, but sorry, I'll explain these a bit more. So we essentially thought that wave height was hypothesized to be correlated with these discrepancies, leading to this method of data representation here. To put it briefly, wind speed observations for ERA 5 were selected based on significant wave height and the same time and dates as the wind speeds were plotted. So this includes OI and ERA 5 wind speeds plotted for the bottom 25 percentile of significant wave height. As you can see, 1-to-1 relationship in this case. But then we actually have a slope increase with higher significant wave height. So this image here is 25 to 75 percentile of significant wave height. And then this is 75 to 100. So as you can see, gradual increase in slope. And I think this image shows it a bit more directly as well. So the red and green lines represent the Kara and ERA 5 wind speeds respectively. And then the much higher slope attributed to the blue line represents the OI buoy, which further indicates the growing disparity between wind speeds and the reanalysis models. So in conclusion, what does this all mean? It can be concluded that the Kara's model's high resolutions tends to be more reliably detailed for 10-meter wind speeds in close proximity to variable topography, which was kind of that first or the second figure I showed. But over lands and over the open, or over flat terrain and over open water, no differences. But there actually might be quite the difference for significant wave height. So we think wave sheltering is actually leading to higher percentile winds not being accurately represented in the reanalysis models. I hope that was clear. Thank you.
Thank you, Adrien. Okay, so if there are any questions, please put them in the chat box on Event Mobi. And I actually had somewhat of a conceptual question. So on one of your very early slides, you were talking about air-sea heat flux and ocean stratification. I think it was even back a couple from there. Yes, right here, or right there.
Yes.
Perfect. So here you were talking about how cooling of the ocean surface can cause weakening of ocean stratification. But in a lot of parts of the Arctic, we actually have temperature increasing as you go deeper down in the water column. So in that case, if you were cooling the surface, you'd actually be strengthening the ocean stratification. And I just wondered if you could speculate a bit on how that would change the picture that you're describing in this slide.
That's interesting. Is this during summer months or?
No, it's when you're in the central Arctic basins, the warm, relatively speaking, warm Atlantic water comes in but the stratification is mainly set by salinity, so you can actually have warm water below cool water.
Interesting. Okay, I'll admit I don't know too much about it. I just yeah, was studying wind speed, so yeah, sorry.
Yep, no worries. And I do have a question from Amber. Curious if you know if anyone has used these data to force an ocean model and looked up biases in the ocean.
Can you repeat that, please?
So she's curious if you know if anyone used these data to force an ocean model and to look at the biases in the ocean.
Not sure. Not sure.
Okay. Okay, so we do have a couple more minutes for questions. And then after that, we are going to move on to Lee's talk.
Go to share screen.
So Lee, if you want, you can start getting set up.
Sure. Okay. I think I have to switch the. Is it good now, Hayley?
Yes, that is looking great. So let me just check if we have any more questions,
Sure.
and then we can get started. Okay, so I think we are going to move on to our next speaker. So our speaker now is Lee Zhai. And Lee, whenever you're ready, you can go ahead.
Oh, thank you. Thank you very much, Hayley. Yes, today I'm going to talk about the variations of marine heat waves and cold spells in Northwest Atlantic during the last 30 years. This study is a contribution to the Nice Copernicus Ocean State Report. My co-authors of this work include Youyu Lu, Haiyan Wang, Jill Garrick, Simon Van Gennep. So first, I'd like to give you some examples. So why we care about heat waves or extreme temperature events. So, and then I will provide some definitions of marine heat waves and cold spells. Then I will present some results derived from GLORIOUS reanalysis and model validation using satellite temperature and mooring observations. In the end, I will give some conclusions and discuss plans for the future work. So my first example is about how the extreme heat event affect the farmed Atlantic salmon in a fish farm in Liverpool, Nova Scotia. So from this study, this is a master thesis, and the student found that when temperatures is below 2 degrees and above 19 degrees, the Atlantic salmon is under thermal stress. So from this figure, you can see when they're under extreme heat event, so the Atlantic salmon actually was able to increase their heart rate and reduce their activity levels. So the second example is about how the heat event affects the snow crab fishery in the southwest Nova Scotia. We all know that snow crab distributions are constrained by the available thermal habitat. So from this figure, you can see the red shaded color indicates temperature is not suitable for snow crab. So you can see that in 2011 and 2012, and this warm event negatively impacted the snow crab juvenile stages, and this resulted in a temporary decrease in abundance of snow crab on the southwest Nova Scotia. The last example is about, so this record temperature in 2012 actually had an opposite impact on the lobster fishery in the Gulf of Maine. So the extreme temperatures caused lobsters move inshore earlier in the spring in Gulf of Maine. And then this enhanced lobster growth extended fishing season and supported record landing of lobsters in the Gulf of Maine. As you can see from this figure here, the gray color shows this record landing in 2012. So all these examples motivated us to further quantify both heat waves and cold spells in Atlantic Canada. So first we need to define climatology. So here we used daily temperature average over 30 years from 1992 to 2022 to define a climatology. So then we need to define the threshold. So we used the seasonally varying threshold. So for marine heat waves, we used 90th percentile, and for marine cold spells, we used 10th percentile. So the extreme events has to last for at least 5 days, and 2 extreme events needs to be 2 days apart. So later on, I'll show you some metrics to characterize those extreme events, including frequency, mean intensity, and total days. So here we're using a MATLAB-based tool to detect extreme temperature events. The data sets used in our study include daily 112-degree glorious reanalysis, 1/4 degree satellite sea surface temperature, and mooring observations at a location near Station 2 on Scotian Shelf. So first, I just want to show you some example time series at this mooring location indicated by the red dot in this figure. So left 2 panels shows the surface temperature time series from glorious on the top and from CSST on the bottom. So clearly you can see there are some cold events in spring and some cold events in winter time, all captured very well by glorious. And the middle 2 panels shows the sea surface temperature in 2012. So clearly you can see there are a lot of heat events in 2012. As we all know, 2012 is a very warm year, and all these warm events were well documented in the literature. And those events mainly driven by the air-sea heat fluxes linked to the jet stream variability. So here I just want to highlight there is a long-lasting marine heat wave, kind of from June to the end of August. So both shown in the glorious and the satellite SST. So the interesting is that the termination of this heat event was actually caused a coastal upwelling on the Scotian Shelf. And this figure here shows the various preserving spectrum from glorious SST in blue and CMC SST in red. So clearly you can see glorious reproduce reasonably well, very well actually, the both seasonal and subseasonal variations of sea surface temperature. So this figure here shows you the bottom temperature in 1997. You can see there is 2 cold events in January and December, and they are the actually cold spikes identified by my colleague Mike Casey, and he showed those cold spikes are driven by the intensification of Nova Scotia current flowing southwestward along the coast of Nova Scotia. And then this figure here shows you the bottom temperature in 2012. The red color shows the mooring observations. So clearly you can see glorious captured those warm events in late fall and winter, even though glorious did not simulate those cold spikes observed in this mooring data. So this figure here shows you that glorious overestimated the seasonal variation and underestimated subseasonal variation of bottom temperature at this mooring location. So we suspect this may be related to the climatological river runoff used in glorious reanalysis. So I think further investigation is needed to explain this difference. So here I'm showing you some spatial distribution of a marine heat wave characteristics from a derived from glorious reanalysis. The top panel shows the surface marine heat waves. So this figure here shows you that the marine heat wave frequency. So on average, there's about 1 to 2 events on the shelf, whereas there's about 2 to 3 events in the deep water. And this figure here showing you that marine heat wave total days range from 20 to 30 days in our study region. But there are some interesting features here. And you can see along the path of inshore and offshore Labrador current, the total days, you have less total days compared to the surrounding areas. And this figure shows the marine heat wave mean intensity shows very strong contrast between the shelf water and the slope water. And this is likely due to the strong temperature variations in the slope water. So the bottom three panels shows the bottom marine heat waves. So if you look, this one shows you the frequency, and you can see, so the spatial distribution of the frequency, bottom marine heat wave frequency is strongly affected by the local bathymetry. For example, in the deep basins, such as Emerald Basin on the Scotian Shelf and deep channels, these Laurential channels, the marine heat waves occurs less frequent compared to the surface marine heat waves. And this one shows here the bottom marine heat wave total days. And if we focus on the Scotian Shelf area, and you can see that bottom marine heat waves last longer compared to the surface ones, and have stronger intensity compared to the surface marine heat waves. And we think this may be related to the different forcing mechanisms. So at the surface, you have air-sea heat fluxes, so they're more efficient at accumulating and dissipating heat in the upper water columns, whereas at the bottom, so the heat waves is more affected by the advection process, which has occurs at much longer time scales. So here the figures shows you the spatial distributions of marine cold spells. So if I flip the figure back, heat wave and cold spells, and you can see the spatial distribution are very similar. So this indicates that the frequency distribution of temperature anomaly are close to normal distribution. So now we're looking at the interannual variations of heat waves and cold spell total days at this mooring location. So this figure shows that the surface marine heat wave total days, and you can see there are more than 200 marine heat wave days in 2012. So that's in that extreme warm year. And you can also see there's strong interannual variations, and there's this increasing trend of the marine heat wave total days. And this figure here shows you the surface marine cold spell total days. And you can see strong interannual variations and a decreasing trend. And both the surface marine heat waves and cold spells are strongly correlated to the annual mean sea surface temperature shown in this panel here. And the correlation is between 0.8 and 0.9.
2 minutes.
Oh, thank you. For the bottom marine heat waves, we can see there is a regime shift in around 2012. So before 2012, you hardly see any marine heat waves, whereas after 2012, so on average, you get about 100 days of marine heat wave days every year. And the same thing you see, there's this regime shift in the marine cold spell total days. And again, the bottom marine heat wave and cold spell total days are strongly correlated with the annual bottom temperature. And you can see this mean temperature shift from about 8 degrees before 2012 to about 10 degrees after 2012. And we also found there's a weak correlation between surface and bottom marine heat waves, and no correlation between surface and bottom marine cold spells. And again, this probably caused by different forcing mechanisms. So as one of the requirements in this state report is to include 2023 data. So here I just want to show you the surface temperature in 2023. And you can see there is a warm event in January. And this is caused by extremely warm air temperature in January. And then this event was terminated by a cold air outbreak identified by my colleague, Mike Casey. And in the summer, you can see there are some short-lived warm events, and which is terminated likely by the coastal upwelling. So this figure here shows you the bottom marine heat waves in 2023. And you can see there are some short-lived marine heat waves from January to April. And those heat waves kind of interrupted by those cold spikes here. So we didn't find any cold spells in 2023 at the surface and at the bottoms. So recently, there is AZMP spring observations show that the bottom temperature is continue to decrease in 2024. So our question is, if the regime shift we see at this mooring location will be averted in 2024. So that's why we need more mooring data and glorious data to continue to monitor the state of the ocean. So here I'll let you to read the conclusions. The one thing I just want to point it out, there's a strong debate in the literature about how do we define climatology. Either should we remove or keep the warming trend before we do the marine heat wave analysis. I think the quick answer is that it depends on the applications of our interest. So we may be able to provide the marine heat waves derived using both kind of a fixed or shifting climatology. So our ongoing work includes we'll derive more marine heat wave or cold spell statistics using our Three Oceans Kindcast will be produced by our colleague Xianmin Hu. And we could also explore applications of marine heat waves for ecosystem, which is led by Hui Sheng at DFO. And then we could also quantify forcing mechanisms to better predict marine heat waves and cold spells. Okay, thank you.
Thank you, Lee. That was really interesting. So I have the exact same question as the question that Amber has put in the chat. Can you speculate on why we see a regime shift after 2012?
Yes. So this is okay. So that's linked to the bottom temperature, right? So there's a shift in bottom temperature, and we think it because this location and there is affected by the kind of a slope water inflow from like here. Probably around 2012, there's more like a warm slope water get affected on the shelf. And then maybe the slope water kind of remain warm for like after 2012. And that's just my kind of a suspicion, right? But we need to look for maybe to go back to the glorious and to examine the like a near bottom temperature or temperature at like 150 meters to see how this the water slope water may affect the water at this mooring location. Yeah.
Perfect, thank you. So I think we're right on time to move to our last but not least speaker, Nancy Soontiens. So Nancy, you can go ahead and share your screen and start whenever you're ready.
Great. Great, thank you so much. I'm just going to pull up the slides here, share, and then I'll go here. It's a bit laggy.
Looks good.
Oh, there we go. Okay. Apologies for the delay there. Just trying to get things set up. So thank you very much, Hayley. And good afternoon, everybody. So my name is Nancy Soontiens, and I'm a research scientist at Fisheries and Oceans Canada, and I'll be speaking about marine heat wave conditions covering the Newfoundland and Labrador shelf. And I'm going to be doing something a little bit differently from Lee, where I'm focusing in on 2023. So this work was conducted with a number of co-authors who are also affiliated with Fisheries and Oceans Canada. Right. I'll first provide a bigger picture context by describing the marine heat waves that were observed in the entire North Atlantic in 2023. So Newfoundland wasn't unique in the fact that we had experienced some heat waves. In the animation on the right, you're seeing the sea surface temperature anomaly from the ERA 5 atmospheric reanalysis. So strong positive anomalies in the red and orange colors are indicative of marine heat wave conditions. And these strong anomalies started in the east in the spring and were later detected in the west in July. Now, these marine heat waves received significant media attention, which sparked public interest and raised concerns connected with the rising ocean temperatures and potential impacts on marine ecosystems and weather. So now I'll review how marine heat waves are defined. So in this study, we're using the Hobday et al. 2018 definitions, where the temperatures at a given time of year is compared to its climatological value. So if the temperature exceeds the 90th percentile for at least 5 days, then the marine heat wave is detected. And the severity of the marine heat wave is characterized by the degree to which the temperature deviates from that 90th percentile. So here we're considering 4 marine heat wave categories, ranging from moderate in the yellow, and then to extreme in the dark red. Now we're using sea surface temperature data from the GLORIES 12 ocean reanalysis to characterize the marine heat waves, and we're using a 30-year climatological period from 1993 to 2022. And this period was selected mainly because of the availability of the reanalysis data. And we complement this data with the winds from the ERA 5 atmospheric reanalysis and also observations collected under the Atlantic Zone Monitoring Program. The area considered in this study is the Newfoundland and Labrador shelf, which is defined by the white polygon in the plot on the right. We investigate marine heat wave conditions by averaging the sea surface temperature over this entire region. And we also explore temperature and salinity conditions along the 2 transects shown in blue. This is Seal Island in the north and the Flemish Cap in the south. And those temperature and salinity values from GLORIES 12 are compared with data collected under AZMP, which samples these transects up to 3 times a year. And in addition, Station 27, which is marked by the white circle, is a high frequency sampling station. It offers another point of comparison between observations and reanalysis. So although not discussed in detail, in this presentation, we've also conducted the marine heat wave analysis over the 4 subregions denoted in the plot on the left. So these are Labrador Shelf in the north, the Northeast Newfoundland Shelf, and then the Grand Banks, and then Flemish Cap. And these regions were selected because of their unique ecosystem characteristics. So just as a quick summary of those results, the Flemish Cap region received the strongest marine heat wave in July and August. And the Labrador Shelf and Northeast Newfoundland Shelf were the 2 regions who received marine heat waves in October. Now together, these 2 plots show an overview of the spatial extent of the marine heat waves, which covered a very large area. The first plot on the left shows the highest marine heat wave category between July and October. And on the right, we're seeing the total number of marine heat wave days. So our goal in our study is to describe some of the factors that contributed to the evolution of these marine heat waves. Now, first, we'll take a quick look at the monthly average sea surface temperature anomalies, which showcase how the marine heat waves evolved. So the red values indicate warmer than usual conditions, and the blues show colder than usual conditions. So first is that cold anomalies are noted on the Newfoundland and Labrador Shelf in both May and June, but those anomalies transition to warm in July through October, and those warm anomalies cover a very large portion of the shelf. And of note are the very strong anomalies over Flemish Cap in July, which reached values up to 5.5 degrees Celsius. And although not shown here, those cold spring conditions were accompanied by some unusual ice conditions as well, where there was sea ice coverage that was stronger than usual, but later in the season, and there was still ice cover in June. So moving on, we'll explore the vertical structure of the anomalies along the Seal Island and Flemish Cap transects. So the shaded contours show anomalies from GLORIES 12, and the vertical stripes show anomalies from the AZMP data, which was collected in July and just happened to coincide with the time of the marine heat wave. In the top panel, both the reanalysis and observations are showing a shallow layer of warm anomalies extending to about 10 to 20 meters in depth. And beneath that warm layer, there's a layer of colder than usual subsurface water. In addition to the warm anomalies in the surface, we also see strong fresh anomalies in the surface, particularly at Seal Island in July. So here the fresh anomaly extends 20 meters or deeper and is strongest over the shelf break. So that's in the bottom set of panels. And at Flemish Cap, there are also surface fresh anomalies, but in this plot, they're not quite as apparent as later in the season, and they're not as strong as what we see at Seal Island in July. So next, we'll characterize the evolution of the depth average temperature and freshwater density for several different depth bins. So here we compare the 2023 climatological, the 2023 values to the climatological mean, which are shown in the dashed lines, and the 10th and 90th percentiles in the shading. And the gray shaded rectangles represent surface marine heat wave periods when the temperatures are averaged along each of those transects. So I have a number of different depth bins here, but I'd like to draw your attention to the blue and the orange curves, where the blue is the surface value and the orange represents the 0 to 20 meter depth bin. In the top panels, we see that Seal Island experienced 3 surface heat waves during the summer and fall. The first in mid-July to early August, the second in mid to late August, and the third in October. And by comparing the blue curve at the surface to the orange curve, which represents an average over 0 to 20 meters, we see that the July marine heat wave was mainly confined to the surface, whereas in August and October, the 0 to 20 meter layer would also have been considered a marine heat wave. And at Flemish Cap, the surface heat waves were in mid-July and early August, and then in mid-September. Early to mid-September. And once again, the July heat wave was mainly confined to the surface. Now, at the panels at the bottom, where we're examining the freshwater density, we see unusually fresh conditions exceeding the 90th percentile throughout most of the summer and fall. And at Seal Island, the freshwater peaks in July, and Flemish Cap, it peaks a little bit later in August. And early in the summer, the fresh conditions are more confined to the surface than later in the fall. So next, I'd like to explore some of the factors that contributed to the surface marine heat waves in 2023. And to do so, I'm plotting in blue, the 2023 time series of the average sea surface temperature over the Newfoundland and Labrador Shelf region as compared to the climatological mean in black, and the 10th and 90th percentiles in the gray dashed. And the marine heat wave periods are shaded in gray. So when averaging over this large area, 3 periods are highlighted: July and August, which was the longest and most intense, September, and then October. And as noted previously, that October marine heat wave was in fact mainly observed in the Lab Shelf and the northeastern Newfoundland shelves. So I'll be next exploring how some factors like winds and stratification are linked with these marine heat wave periods. So first, stratification. Here we're plotting the vertical maximum of the squared buoyancy frequency at station 27, calculated from GLORIES 12. And the 2023 time series is again in blue. And as before, the climatological mean is black, and the 10th and 90th percentiles are gray dashed. And higher values mean that the water column is more strongly stratified. And we also compare the stratification from the AZMP data in the brown dots, where the dark brown indicate 2023 values and the lighter brown are from the 1993 climatological period. And during the marine heat wave periods in gray, it's clear that the water column is typically highly stratified, often exceeding the 90th percentiles. And the strong stratification may be a factor contributing to the intensity of the marine heat waves, as a more stratified water column is less prone to vertical mixing and redistribution of the heat forcing at the surface.
2 minutes.
Thanks. So another factor that impacts stratification is the amount of energy available to initiate vertical mixing. So we looked at the 10-meter wind speed at station 27 from Era 5 atmospheric reanalysis, and stronger wind speeds can cause more vertical mixing near the surface. So as seen in this plot, the start of the marine heat wave periods are linked with periods of lower than typical wind speeds. And in addition, the marine heat waves tend to end when wind speeds return to high or more typical values. Next, we'll take another look at the depth average temperature in the near surface layer from the 0 to 20 meters. And this time it's averaged over the entire Newfoundland and Labrador shelf. And as we saw at Flemish Cap and Seal Island earlier, the marine heat wave conditions were very concentrated near the surface in July and August, but penetrated deeper in September and October. And this is evidenced by the fact that the 0 to 20 meter layer does not reach the marine heat wave threshold by exceeding the 90th percentile in July and August, but it does in September and October. And so lastly, the unusually fresh conditions observed in the 0 to 20 meter layer at the Seal Island Flemish Cap transects are also apparent in the 0 to 20 meter freshwater density averaged over the entire Newfoundland and Labrador shelf. And the freshwater density is high throughout most of the year, but particularly from July through September and throughout the marine heat wave periods. And interestingly, this freshwater density curve from 2023 appears to be shifted later in the year than the climatological curve, where the minimum occurs about a month later than what is typical. And this shift might be associated with that unusual trend I noted earlier in the sea ice coverage, where there was a slow start to the ice covered season and a later retreat on some parts of the shelf. All right, so in summary, the 2023 marine heat waves on the Newfoundland and Labrador shelf were preconditioned by an unusually cold spring. The marine heat wave periods were associated with high freshwater content, lower than typical winds, and strong stratification. We also have ongoing work characterizing the sensitivity of the marine heat wave metrics that are applied in this study to that choice of the climatological period. So that was noted that there's some debate in the community right now about the selection of the climatology. So we're going to dig into that. And then finally, we'd like to, or there's potential to explore how marine heat waves might impact the marine ecosystem. So with that, I'll share the references here and be happy to take any questions.
Thank you, Nancy. That was really good. I was actually just wondering about what you had said about the sea ice and the unusual timing for the sea ice affecting the freshwater. Do you think you could say a few more words about the connections between those two?
Sure. Yeah. So I think like one of the main drivers of the restratification of the water column is the melting of the sea ice. And so what I speculate, and I haven't looked at this carefully, but it could be that because the fresh water was released a little bit later in the year, that might also explain why we're seeing higher stratification during the marine heat wave periods. And I think there's also a connection. It's just been the last few years, it's just been higher than normal freshwater on the Labrador Newfoundland shelf as well.
Thanks. And just for personal interest, I know that there's some ocean glider data that's collected as part of the AZMP program. Do you know if anyone happens to have compared that with the Glorious 12 output?
That's on the to-do list. It's not quite there, but you're right.
Fantastic.
Fred Sear, he runs a glider program, and he samples one of the transects, not the one I showed, but yeah, we're hoping to run that comparison soon.
I'm very happy to hear that. So Amber had a question. Any plans to look at acidification and oxygen?
No, I have to say not any immediate plans. I think those are really good questions. I know that, again, Fred Sear has looked at some ocean acidification data based on what's been collected in AZMP, but and I think he has a publication out, but besides that, I'm not aware of any of that work happening.
Okay, so we are basically at time, but if anyone has any last minute questions, feel free to throw them in because Nancy was the last speaker for this session. And I just want to take this opportunity to thank all of our speakers again, both in this session and this morning session, on behalf of myself and Amber. And just say thank you to everyone in our audience today. We've had fairly consistent numbers for both sessions, which is great to see. So thank you all for taking the time to join us on the last day of CMOS. And we hope that you enjoy the rest of the conference. And I think with that, we will close the session.